Hello and welcome to today's webcast. My name is Jimmy Carroll. I'm an editor for Vision Systems Design. The speaker for today's event, The Growing Need for Precision in LED Lighting, is Win Harden, who leads the marketing activities at Smart Vision Lights through his agency, Tech B2B. Win regularly writes and speaks about the state of the machine vision, automation, and robotics industries, and is filling in today due to a scheduling conflict for Paul Powers, Director of Sales, Americas, at Smart Vision Lights. Before we begin, we wanted to cover a few housekeeping items. If you have any questions or issues during the webcast, you can click on the Ask a Question area of the console. We'll try to answer as many of your questions today as possible. If you have any audio issues, please try refreshing your page. If this doesn't work, or if you have any other issues during the webcast, again, please click the Ask a Question area of the console, and a member of our webcast support team will work with you to correct the issue. For your convenience, this presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent to all registrants with the link to the archive, and it will also be accessible from our homepage. Today's slides will also be available for download, and these can be accessed via the Event Resources tab under the Ask a Question area. Before we begin, we'd like to thank our sponsor, Smart Vision Lights. Now it gives me great pleasure to introduce Win.
Hey everybody, this is Win Harden. Thanks for inviting us in today. Jimmy, we sure appreciate being part of today's webinar. So we wanted to put together a presentation on the hot trends that are affecting the machine vision lighting industry, and specifically solid-state LED lighting. As you can see from the topic, we've got the growing need for precision in LED lighting, and those will be the discussions we're talking on today. Now, what we're looking at here is a picture of the National Ignition Facility at Lawrence Livermore National Laboratory. Now, NIF hoped to deliver multiple laser pulses to a nuclear target, each arriving within picoseconds of the others, all to generate the world's first sustainable fusion reaction. It hasn't worked yet, in part because of the difficulty in controlling light with that sort of precision. Luckily, the machine vision industry doesn't need picosecond light control, but we're moving in that direction. As you'll see in this presentation, in response to faster frame rates and other CMOS advances, traditional microsecond switching times for LEDs are moving to nanosecond precision control for drivers that are up to the task of managing this new capability. This presentation will also discuss 3D and multispectral imaging solutions as they continue to gain in capability and fall in price, a number of exciting things in that area. And finally, we'll look at the need for LED light manufacturers like Smart Vision Lights to adapt and to use more advanced optomechanical electronic modeling and design programs than we have ever before. And this is so that our products can fully utilize new optical materials that can deliver the precision control that the machine vision industry needs to solve a growing body of more complex applications. Many of those applications far beyond the traditional industrial plant floor, so we're talking about agriculture, logistics, service robotics. Okay, so freezing the motion of fast-moving objects with light in a camera isn't quite as exciting as Kylo Ren using the Force to catch a laser blaster pulse in midair. It's a lot more common in the world of machine vision. Bottling lines regularly move past inspection stations at the rate of hundreds of units per minute, requiring approximately 5 image acquisitions per second, which doesn't sound too bad, but to avoid blur, the system integrator doesn't have a few tenths of a second, but rather a few hundred microseconds at the most. For another example, high-speed microscopy uses 100 frames per second CMOS cameras to capture the movement of live cells and unfolding proteins, while high-speed cameras, operating in the thousands or tens of thousands of frames per second, are widely used with machine vision software programs such as those from Norpix to analyze high-speed production machinery and troubleshoot problems that happen too fast for the eye to see. Last week, we got a call for a strobe light that could generate a 400 nanosecond pulse for just such a high-speed analysis project. Requests for strobe lights that can operate at 5 to 10 microseconds are becoming commonplace, which doesn't give the light much time to turn on and off because most drivers take just a few microseconds just to come on. The result is that the system designer needs to test the camera and light configuration along with the entire system to see how much they must advance or retard the trigger signal so that the light will be at full power during the desired exposure period for these high-speed applications. And then if there's any changes to the system after commissioning, such as cable length, a light replacement, or even possibly changes in environmental conditions, any of these could adversely affect the system's ability to perform, all because the light can no longer halt time from the camera's perspective. This slide shows the challenges of matching light pulses to camera acquisition via trigger signal when pulse durations and timing accuracy drop down into the single-digit microseconds. While the digital trigger pulse calls for the light to be on 10 microseconds, the driver takes 6 to heat up and to raise the LED to full output. If the light follows the trigger signal, the light will only be on for 4 microseconds instead of the desired 10, requiring the designer to spend additional resources to advance the trigger signal to a time at 6 microseconds prior to camera exposure. And again, these numbers can change as the conditions of the system change too, or the components or the environmental conditions. And let's note that this is not due to the LEDs, but this is to the electronics that are driving them. Standard LEDs have rise-fall times, or the amount of time for when the power is turned on, that's electrical power, before the photons start coming out, and the time between turning the power off and the last photon is emitted, of approximately 10 to 100 nanoseconds. Visible lights average around 100 nanosecond rise-fall times, but infrared LEDs have faster switching speeds, which is helpful considering the number of inspection systems using infrared illuminators to either avoid light pollution on the plant floor or as part of a growing segment of multispectral imaging systems, which we'll discuss briefly later in the presentation. The key to developing faster drivers is in the MOSFET, or the power components that deliver electricity to the light. Smart vision lights will soon have a nanosecond scale driver, following our industry introductions of the first internal overdrive strobe driver, and more recently, the industry's first internal multi-drive driver, which is capable of continuous or strobe operation using the same internal electronics. One of our differentiators at our company is universal internal drivers. And if you happen to be going to Stuttgart later on this fall, you will be able to see the first LED driver that's working on nanosecond scale times. At least that's what we're told from engineering. And we got to believe them, because they're engineers. Now, the second section of this presentation is to look at color, and we're going to go into multispectral a little bit. Let's see how LED lights are impacting advanced color machine vision applications. This image shows how different color illumination can significantly change the perceived color of an object. In this example, 3 colored spots, red, green, and blue, illuminate a white screen. A hand is placed between the screen and the lights, casting overlapping shadows on the screen. You can see the many instances of color mixing in this picture, illustrating the principles of color subtraction and addition. Now, multispectral or hyperspectral systems are also color machine vision solutions. These systems take into account the available illumination spectrum, precision spectral profiles of reflected light, and by association absorbed light, light that was not absorbed by the material at hand, but it was reflected back to the sensor, at key wavelengths, and then it generates large data sets that can tell a great deal about the physical property of an object based on the light-object interaction. While hyperspectral and even multispectral imaging has been cost prohibitive for nearly all industrial applications in the recent past, new multispectral cameras such as Teledyne DALSA's Piranha 4 Quad Linear Multispectral, the IMEC Multispectral Sensor, which takes a standard area array and places band gap coatings over each row, so effectively turning an area array sensor into a linear array sensor, each line sensitive to a certain part of the spectrum, generating hundreds and hundreds of different frames based on the size of the array. Unfortunately, it's not cost-effective yet, but I think we're all very impressed with what was initially shown a few years ago. In addition to this, there's actually a third camera which is finally coming on the market that I'm actually very excited about. And I'd be remiss to not mention JEI has some excellent RGB plus near cameras in there as well. But Teledyne DALSA, I believe, has just released, or at least in Asia, the Linea TL. And in this case, instead of taking 4 different sensors and applying optical coatings to each sensor so that it's sensitive to a very specific narrow spectral band, what Teledyne has done is they're using the time domain to separate the various spectral bands. So you don't have to put a coating right on the sensor. You don't have to spend all that extra money making a customized sensor. And if you want to change the spectral bands that your imaging system solution is looking at, you simply change the light from your illuminator. So the sensor is on, and we shoot it with a very limited band, red light of a certain gap. So the camera acquires the image of the spectral response within that spectral band, and then we fire the next light, and we fire the next light, we fire the next light. And we take all those images. As long as it's not a high-speed, high-throughput application, we've taken a multispectral solution, which used to cost many tens of thousands of dollars, and brought it underneath $10,000 for a total solution. And then if you add in the ongoing drops in computational costs, more designers are able to take advantage of precision color as a way to inspect and to sort goods. At the same time that we're getting seeing interest from multispectral, it's probably not unusual then that we're seeing more interest and availability of shortwave infrared or SWIR cameras. SWIR wavelengths are typically used in the following applications: inspecting fill levels of non-transparent containers thanks to the penetration of infrared light through certain tissues and materials. Find hidden moisture in packaging. One of the things that infrared is very sensitive to is water absorption. Water just absorbs infrared light like crazy. So when we're seeing a bruise, for example, in the apple that we're looking at on the screen, what we're actually seeing are a difference in water density in that space. We can use SWIR to look at, inspect tamper-proof security codes, locate damages fruit, as we've said, gauge relative water in plants, something that Smart Vision Lights has worked extensively with Michigan State University on recently, verification of coating or dryness uniformity in bulk materials, anti-counterfeiting inspection, glass inspection, surveillance, wafer and solar cell production, and locating objects that are behind smoke, steam, or fog due to infrared's ability to penetrate air with particulates and contaminants. Now, traditionally, black body or halogen lamps have been the illuminators of choice for anything longer than near infrared, which has been served well by the LED industry for many years since the advent of optical fiber communications. And the reason being was because that near infrared LEDs were the initial pumps for optical fibers used in telecom. However, in recent years, LED chip makers have refined their semiconductor manufacturing processes until dies with reasonable output and yields now make other non-visible parts of the spectrum viable for machine vision applications. And there's also been the addition of at least one, I believe, maybe two new SWIR sensor fabs around the world. So we're seeing more availability of the in-gas sensors themselves. This is when you coupled with high output LEDs in the SWIR space, and the utility, the ability of infrared for doing material science and spectrometry. There's just a lot of along with the incredible computational power that we all have for cheap now, we can finally look way beyond the visible spectrum and solve applications that we weren't solving before. Much like deep learning in some way is helping the software industry and machine vision to do the same thing. The challenge for machine vision customers today is to find the best wavelength to illuminate their SWIR multi or hyperspectral imaging system. That's why some LEDs OEMs offer multicolor test boxes to help designers evaluate which wavelength works best for their application. What about other parts of the spectrum, in particular mid-wave and long-wave infrared, where so much spectrometry is done to determine material properties? For these applications, machine vision lights need to be able to deliver multiple wavelengths of light from the UV through visible into near, short-wave, mid-wave, long-wave infrared. Now, there's exciting work being done right today that uses cascading semiconductor lattices to enable LEDs with emission spectra tailored to very specific customer needs. Now, while machine vision applications do not represent a large enough application base to drive the development of these new mid-wave and long-wave emitters and even into the terahertz and microwave regions of the spectrum, there are many applications in life sciences and wearable devices that are banking on compact infrared LED light sources. So as usual, the machine vision industry isn't driving the development of these new LED wavelengths, but we are going to benefit from these consumer applications that are going to use the same components. Part of a machine vision lighting solution for multispectral 3D and large area applications includes greater light management. Traditionally, machine vision integrators were content, actually often strongly resisted the need to put anyone else in charge except the PC or the smart camera. The PC or the smart camera should always be in charge of all the lighting triggers and controls, and it's understandable why that was the design preference. However, as the number of lights exceeds the I/O capability of a standard smart camera, light managers become either necessary or cost-effective compared to a frame grabber for a PC host solution. For example, a standard solution for a 3D vision system is to use multiple cameras in a stereo vision configuration, which is expensive. Or you can mount a single camera on a movable platform, such as a robot, take multiple images, use your machine vision software to determine perspective changes, and then deduce the 3D surface cloud based on those variations. But the same can be achieved for a fraction of the cost by using multiple lights with a single stationary camera as part of a photometric 3D solution, for example. Basically, if you're not familiar with photometric 3D, the lights are placed around the area of interest, and it has to have some raised 3D component to it, of course. The shadows or the changes in textures caused by illumination from different directions are then combined into one image, which offers far better resolution and contrast than any of the originals. Light managers are going to give designers more options for designing cost-effective solutions for common industrial applications, just like it's for whether it's color vision or whether it's 3D vision or vision-guided robotics. Now, right before we go into our next section, I think it's probably a good time. Janelle here is going to push out a poll to all of you guys who are listening right now, and ladies, excuse me, please. And the question is basically related to what should be in charge with the machine vision system. Should it be a camera PC or lighting system or something else? If you wouldn't mind taking a quick second and just poking an answer, yes or no, on the poll. If you have some additional thoughts you can share with us, that'd be great. Hopefully we'll get to share some results with you before the end of the presentation today. Let me see. Actually, I believe I skipped one. Popping back real quick. Forgive me. Fast buttons. So in the last part of this presentation, we'll look at how lighting precision is changing the way LED light manufacturers develop their products. We've been talking about precision control. Precision control requires better design and better testing capabilities, especially when it comes to custom solutions. As we continue to demand more from our machine vision lights, leading OEMs are adopting multidisciplined electro, optical, mechanical design methodologies and advanced optical testing techniques that enable us to not only achieve new levels of performance, but to do it in a format that is both compact and reliable, and maybe more important to everyone on this call. In addition to those, compact reliability costs are obviously our key, but we can also do it quicker. We can develop prototypes and custom lights far quicker, and by doing really tight simulation, deliver real-world products that are performing pretty much exactly as we predict them during simulation. Sorry, I'm bouncing everywhere, guys. So at Smart Vision Lights, we use the latest optical, mechanical design tools to develop innovative solutions in lighting. Multidisciplined design approaches allow us to quickly develop and test our product concepts, reducing our time to market. And it's also one of the reasons why Smart Vision Lights was the first to offer a 10-year standard warranty for 99% of its products. So our UV lights and others, where the semiconductor and the basic materials still are in development, those are the few lights that we don't get covered with our 10-year standard warranty. Optical and mechanical designs can be quickly passed back and forth between ZMAX and SolidWorks. In many cases, our die makers provide files for optical simulation, which is helpful. These files can be imported into ZMAX and included in an assembly for simulation, which allows for quick model development. And then after the desired optical and mechanical parameters are determined, our parts are sent out for manufacturing. And then by combining optical simulation with the mechanical design process, the finished product will match the intended optical design goal. Some of the other changes we've made recently is the use of, we've included some CNC machines so that we can do really fast enclosure turnarounds for prototyping systems. So we're really proud of that. And one other important aspect, and that gets into testing. In addition to having optical engineers on staff, that are helping our electronic engineers and to develop innovative products. We've also been leaders in testing. In-depth testing is the best way to evaluate the effectiveness of a design and guarantee customers that our light coverage patterns, wavelength, and intensity are up to what they need. And this is particularly important for CE certification and compliance with new LED photobiological safety standards such as IEC 62471. And if you're not familiar with IEC 62471, it's a photobiological standard that basically says infrared and UV light is dangerous. As LED lights become more and more powerful, it's a subset to a laser safety class standards, which are also designed to protect eye safety. If you're not familiar with IEC 62471, I encourage you to do a little bit of research and look at it. It's actually, it must be done to be able to get a CE certification on your product. And if an injury was to result from a product that had a CE certification on it, that couldn't back up the testing, there's a possibility that all those lights from that line could get pulled, and any production equipment would be without its illumination source. Now, I hope you've enjoyed this presentation. In short, Smart Vision Lights believes that primary LED lighting trends include faster switching, precision color and light management, and all of this necessitating new materials and design methods. One of the things I didn't touch on briefly, but there's an interesting white paper on our site right now about the use of silicone optics, which we have moved towards. If you're not familiar with silicone optics developed by Dow Corning, it's a quasi-fluid material, optical material that you can make complex optical designs. It has far more better thermal stability than acrylic does. The lenses themselves have a soft feel to them, so they're less likely to shake loose because of vibration, and you can use clip-ons instead of glue, which allow you to put the optic directly on top of the die, capturing more of the light. So there's less loss, and then, of course, better control since you can do complex optical designs. Thanks for your attention today, everybody. I hope you found this presentation useful and informative. I'll be happy to take any questions.
Thank you, Win. So we'll begin our Q&A. So if you have a question, you can use the Ask a Question area of your console to go ahead and get that in. I should note that if anyone has any questions that they'd like to ask off air, they can reach out to myself, and my email is jamesc@penwell.com, or they can reach out to Win directly. So we'll ask a question here that says, can solid-state lighting be an illumination source for multispectral or hyperspectral lighting? Why or why not?
I wish this was a panel discussion, really, for this one to get shot at me, because there's been a couple of introductions recently of even hyperspectral lights, solid-state lights for hyperspectral applications. For those who are familiar with hyperspectral and multispectral imaging, it's really important that you have an illuminator with a very flat, continuous light profile spectrum across your area of interest for your sensor. Solid-state lighting is the antithesis of that. It develops. You design your semiconductors and to emit within a very narrow spectral band, so you try to put multiple colors together and then vary the intensities a wee bit so that you can try to, at the top, have a fairly flat light spectral profile for your hyperspectral imaging system. Now, I think for multispectral, you can pair those lights with the individual sensor requirements without having to do significant back-end processing to normalize the intensity of the different illuminating channels. When you try to, because each one of those channels, depending on what spectral output, you're mixing different lights, so it's going to be tricky. You're going to have a lot more knowledge up front about the light's condition, what it's putting out, so that your measurements on the back end of absorption or reflection are accurate. When we go into hyperspectral, and now we're not trying to balance 4 channels or 5 or 6 channels, but literally hundreds of channels across a very broad spectrum, I think that challenge probably will best be solved by the advent of lattice cascade type LEDs. I think it's going to be a challenge for solid-state lighting to have for precision hyperspectral imaging. However, there's a lot of applications where simply qualitative data is sufficient. That this is more red than that, or this spectral band weighting of multiple spectral bands. And then finally, the final thing I would say is that in hyperspectrals, as we all know quite well, most of the time hyperspectral is used for prototyping of systems, and a multispectral optimized system would be what is fielded commercially. So I think we'll probably still expect halogen to be our best prototyping tool for some period in the future with our hyperspectral, but that solid state can definitely serve a cost-effective illuminator source for multispectral solutions, as long as the system is carefully designed.
Thank you, Win. This next question says, will the new LED drivers work with 95 to 98 CRI LEDs for color measurement?
I have been told no reason why they wouldn't, that there would be any particular limitations in terms of the dyes we're using. But that being said, I would very much like you to get your information to Jimmy so that I can make sure and definitively get an answer for you and follow up on that.
Yeah, and a good point to just spell my email out one more time. It's jamesc@penwell.com. Feel free to reach out with any questions. So let me jump into the next question here, which says, what is the minimum FWHM we can get on UV, visible, and IR LEDs?
Well, you're going to have different values for each one of those. Again, I'll have to get those actual values and get back to you. So it'll depend on specific bands, wavebands, what wavebands particularly you're looking for within those spectrals. If you can get us that information, we can get you that data.
Thank you. This question says, is multiplexed RGB lighting cost-effective against a traditional trilinear RGB camera plus white light?
Cost-effective, without question, because you have a much less complex camera design. You're not trying to register multiple sensors in a single frame. You're doing it at time level, but you're doing that all in software, whereas the camera itself is much more simple. So yes, I believe multiplexing in RGB using time domain is far more cost effective. But of course, the question is, it won't be able to solve the same applications that a 4-sensor JAI or a Teledyne DALSA quad is going to be able to do. They're going to operate much faster for faster speeds. You're never going to use a TDI RGB multiplex solution for a waterfall application, for example, where you're trying to spot rocks in a constant stream of beams. But if the product is moving slow enough and gives you the time, affords you the time to do it, then yes, I think it's going to be very cost effective. And I'm very interested in see how the market responds to the linear TL.
Thanks, Win. This next question says, how much control do you have over specific wavelengths of illumination?
Control do we have over specific wavelengths of illumination? So there's so many ways to tackle that question. I'm wondering if you're asking what percentage of the visible spectrum is currently covered by LEDs, which is 100% of it, but you're going to have certain areas that are going to be more intense than other areas because of material science aspects. So the question, I think I would need a little bit more data to be able to answer that question effectively.
Okay, Win, thank you.
Shoot it to me one more time just to make sure I understand that one completely. Tell me that one more time.
You bet. Yep, it says, how much control do you have over specific wavelengths of illumination?
Yeah, so I think what we're really just talking about is the availability of light from solid-state sources. And yes, if that individual would like to get back to us in terms of if there's specific areas of the spectrum, that would be the best way for me to answer that question for you. If you want to, and then if we want to go deeper into, because there's a lot of ways to manage and control light, not simply its presence and absence, but polarization, light direction, obviously color is important, but so you might have some other questions related to that we could talk about.
Okay, thank you, Win. This question says, what line rates are practical with multiplexed lighting?
What line rates are practical? Line rates are practical. It's a lot of things are going to pay into that. So we're assuming that there's an object, and the object might be in motion. And if the object's in motion, then mass and momentum are going to have a lot to do with how often we can stop the object and then move it before we can take the next image. I think most of the multiplexed, multispectral applications are going to be of non-moving objects. I suspect there's obviously ways. If we could do quick burst 4, but it would be very tight control. If you go to the nanosecond drive rate, it does get to be a very interesting question, though, doesn't it? I mean, we might be able to get to hitting slow motion on movement on the fly. So, you know, you might be able to inspect, I would think, I'm not going to say sub-second, but I think within a few seconds per inspection task routine, excluding software aspects, just on the physical image acquisition part.
Thanks, Wynn. Somewhat related to that, this question asks, when will nanosecond scale drivers be available?
I don't have a hard date on that, but it's not going to be very long at all. And as I said, if you're going to be in Stuttgart, I would very much encourage you to come by our booth where you will be able to see and feel and touch one of our first prototypes. It's my understanding that all electronics are ready, so I would expect we're going to be seeing something very soon. If not by the end of this year, then very early next.
Thanks, Wynn. One of the gentlemen has a follow-up question for you and was curious if he could email you directly, or should I provide him with mine?
Of course. Feel free to share my information, Jimmy. Always a pleasure to speak with anyone.
Okay, so let's see.
Oh, would you like me to share that? Shall I just share it?
Yeah, if you could, yeah.
Okay. All right. It's Wynn, W-I-N-N, at smartvisionlights.com.
Thank you, Wynn. It doesn't look like we have any questions left in our Q&A. I'll just leave it open for a few more seconds to see if anything comes in. And offer one more reminder to maybe have a look at that survey if you haven't already done so.
Do we have any interesting poll results?
Yes, I can push those out now.
Well, I would just like to say thank you for everyone who attended today's webinar. It's been a pleasure, and I hope I can have more conversations, more one-on-one conversations with each of you in the future.
Thank you very much, Wynn. And again, if there are any questions that need further explanation, or if you have a question you didn't want to ask today and you were shy, please do feel free to reach out to Wynn or myself. So with that, on behalf of Vision Systems Design and Penwell and Smart Vision Lights, we'd like to thank everyone for joining us. This presentation will be archived within 24 hours and can be accessed from our homepage. And a reminder email message will be sent to all registrants with a link to the archive. One last time, my email address is jamesc@penwell.com. So we thank you for joining us today and look forward to providing with webcasts in the future.